Good morning, class. I hope you're having a wonderful day. I have uploaded a couple of practice problems to your Canvas account, and I wanted to complete the first one with you. So what I'm going to do is read the problem, underline some important information. I'm going to draw a picture, and I'm going to walk you through the process of part A and B. So let's go ahead and get started. The International Space Station orbits Earth in a LEO, which is low Earth orbit, with a velocity of 7.71 kilometers per second. The mass of the International Space Station is 419,455 kilograms. So in part A, it wants us to calculate the average orbital radius, and in part B, we're going to calculate the orbital time period of the International Space Station. So what let's do is go ahead and draw a picture. So let's say this is the Earth, and we have the International Space Station right here. I'll just label it ISS, and we have a distance identified by R, and this distance is center to center. It's the center of the International Space Station to the center of the Earth. So part A, calculate the average orbital radius of the International Space Station. So we have this thing orbiting the Earth. We're going to start out with the base equation. The orbital velocity of a satellite is equal to the square root of the universal gravitational constant multiplied by mass of the Earth divided by the average orbital radius. So what we're going to do, we're looking for this guy. We want to isolate that on one side of the equal sign, so we're going to square both sides of the equal sign. What you do to one side, you have to do to the other side. Now what's going to happen when we square our square root, the square root and the square are going to cancel. Now what I want to do is multiply by the average orbital radius, multiply by the average orbital radius on both sides of the equal sign. So what we're going to do is multiply by the average orbital radius, and on the right hand side of the equal sign, our average orbital radius will cancel. So it's going to give me average orbital radius multiplied by the orbital velocity squared is equal to the universal gravitational constant multiplied by the mass of the Earth. Okay, now to isolate this variable r, we're going to divide both sides by velocity squared. So you'll see on the left hand side of the equal sign, our velocity squared will cancel, isolating the average orbital radius. Now we can go ahead and plug in some values. So capital G, this is the universal gravitational constant. This is 6.67 times 10 to the negative 11th. And our units are meters cubed per kilogram second squared. And we're going to multiply by the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. And we're dividing by the orbital velocity of the International Space Station squared. Now, we cannot put 7.71 kilometers per second in our denominator here because we need to convert it to units of meters per second. So I have 7.71 kilometers per second. What we're going to do is use some dimensional analysis to convert from kilometers per second to meters per second. So in 1 kilometer, we want to put the units of kilometers in the denominator here, so we cancel the units of kilometers. In 1 kilometer, we have 1,000 meters. So units of kilometers, boom, they're gone. 7.71 times 1,000 is 7,710. And now we have units of meters per second. But don't forget, let's go ahead and we need to square this value here. So let's get out our calculators and let's go ahead and resolve our numerator first, and I just want to talk about the numerical value. So let's start with our universal gravitational constant, 6.67 times 10 to the negative 11th. We're going to multiply by 5.98 times 10 to the 24th. This is going to give me 3.98866 times 10 to the 14th. And let's take a look at our units now. I have meters cubed per kilogram squared multiplied by kilogram. And this is the same thing as saying kilograms over 1. So what we're going to do is cancel our units of kilograms, leaving us with meters cubed per second squared. So meters cubed per second squared. Now in our denominator, we have 7,710 meters per second. Let's go ahead and square that. And this is going to give me 59,444,100. And remember, not only are we squaring the numerical value, we are also squaring the unit value. So meters per second times meters per second is going to give us meters squared per second squared. Now let's go ahead and divide here. And this is going to give me 6709934.2. So 6,709,934.2. And let's take a look at our units. So what we're going to do is divide fractions here. Remember, whenever we divide fractions, it's like multiplying by the inverse of the denominator. So meters cubed per second squared multiplied by the inverse of our denominator. So that's going to be seconds squared per meter squared. So second squared is going to cancel here. In my numerator, I have meters cubed. In my denominator, meters squared. So we get rid of 2 of the meters, leaving us with units of meters. Okay, so the average orbital radius is 6 million. Here, let me write the R. Our variable R represents the average orbital radius for the International Space Station. And remember that this is the center-to-center distance, okay? All right, so we've got our answer for part A. Now what let's do is let's move on to part B. Okay, part B wants us to calculate the orbital time period. Okay, so we're going to use the equation orbital time period, and I'm going to use a subscript ISS to represent the International Space Station. This is going to be 2 pi times the square root of the average orbital radius cubed divided by the universal gravitational constant multiplied by the mass of the Earth. Okay? And we have everything on the right-hand side of the equal sign, so we don't need to do any algebra manipulation at all. We are going to be required to use our calculated value from part A, though. So when we set this up, we have 2 pi times the square root of, we're using this value, our calculated value for average orbital radius, and we're going to cube that value. And then in my denominator, we have the universal gravitational constant, 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. We're going to multiply that by the mass of the Earth, 5.98 times 10 to the 24th kilograms. So in step number 1, I want to cube my numerator, and then I want to take the product of my denominator, and I'm going to put that underneath the radical. So 2 pi. So the 6,709,934.2, I'm going to take that to the third power, which gives me a pretty large value of 3.021028 times 10 to the 20th. Right here we're cubing this, so we're cubing the numerical value and cubing the unit value. So now my units are meters cubed. In my denominator here, our universal gravitational constant multiplied by the mass of the Earth okay, and then just like the previous problem, our units of kilograms will cancel out, and this gives me meters cubed per second squared. Okay, now let's go ahead and resolve this. So let's go ahead and divide. And this gives me, so I have 2 pi outside the radical, then 757,404.241, and I have units of meters cubed over 1 divided by meters cubed per second squared. So remember, when we divide fractions, it's like multiplying by the inverse of the denominator. So meters cubed over 1 times seconds squared over meters cubed. Units of meters cubed, this is going to cancel, leaving us with units of seconds squared. Okay? Let's go ahead and take care of what's under our radical here. So we're going to take the square root of the numerical and the unit value. Okay. This is going to give me 870.289. So I have 2 pi times 870.289. And the square root of second squared is units of seconds. And we're going to multiply this by 2 pi. And that gives me an orbital time period for the International Space Station of 5,468.19 seconds. Okay? Now, that's a lot of seconds. Now, we can just look at this and tell that this is greater than 1 hour, because we know in 1 hour we have 3,600 seconds. But just out of curiosity, why don't we go ahead and convert this into minutes so we can kind of mentally understand, we can wrap our head around the time it takes for the International Space Station to orbit the Earth. So, when we perform some dimensional analysis here, we have 60 seconds. I'm going to put that in the denominator, so my units of seconds will cancel out. And we have 1 minute for every 60 seconds, so I'm going to divide this by 60, and this gives me 91.14 minutes. So the International Space Station makes one complete orbit, or one revolution, in an hour and a half, basically. Okay? So if you have any questions about this problem, just send me an email, and I hope you have a great day.